Good morning, ladies and gentlemen. I'm playing with some old stuff again, and as you can see, I made a tour through our little computer museum, and I picked some highlights, mainly from the CDC and DEC era. And well, we will have a closer look on all these parts, and we will also take apart a little bit of that. Not too much, of course, because it's valuable museum stuff, and I want to keep it as it is. But yeah, we will see what we can do. Let's start with the oldest part of the collection. That's a core memory module from the CDC6004. That's how this machine or its operating console looked like. It has 64 by 64 bits. That means it has a total capacity of 4096 bits. And if we look a little bit closer, we can see the individual bits. You can see here the individual magnetic cores here. That's a core, that's a core, that's a core. And each core will get magnetized in one or the other direction, and it stores a 0 or a 1 bit. And I will explain a little bit later in this video how this core memory is working, but for the moment, just enjoy its beauty. The next item is this beautiful display of 4 modules, 2 from the CDC7000 to 6000 series of supercomputers. They are made in 1965, although the modules here are probably a little bit older. They started in 1964. Okay, and we have modules that look quite similar from the Cyber 160 machine. This is dated 1973. The chips here are from 1974, so that should be more or less correct. By the way, the CDC1604 I showed earlier, the core memory is from 1960. And some additional data. The CDC1604 from 1960 has a clock speed of about 300 kilohertz for the memory, and the CPU was of course a little bit faster. I assume it's a little bit difficult to find any data on this, that the CPU was about 3 megahertz. Now here on the CDC6000 series, the clock speed was already rise to 10 megahertz. It was a 60-bit machine, and that is 1 or 2 of these logic modules. Each module has 64 transistors inside. That's these little metal cans here. We will see that a little bit closer in a moment. So 64, or maybe some more or some less in some modules, 64 transistors here per module. And here in the Cyber 170, almost 10 years later, we already have chips, ICs, integrated circuits. This one is a TTL 7405. That's 6 inverters in one chip. Each inverter consists of 3 transistors, so we have 18 transistors per chip. Maybe some transistor more if there are other chips. We stay with that number for a moment. That gives us 288 transistors. If we have 16 chips, there are 8 on one board and another 8 on the second board here, sandwiched together. So we have 4.5 times more transistors than here. And the Cyber 170 had an operating speed of 25 or 40 megahertz, depending on the model. Here is a wonderful detail view of the CDC6000 module. I don't know what function this module had. There is a number or a letter code on it, but I don't have the manuals to find out what it actually is, but that doesn't matter. It's a couple of gates that were connected with other gates. By the way, they had 8,000 of these modules for the entire 6600 machine. So you can imagine how big that thing was. And that's only the modules. There were a lot of more stuff around it. So we have the transistors here, these little silver cans. There are more transistors behind that. Here are also 2. Then we have a bunch of resistors, a diode, more diodes, that they use the resistors to connect the lower board with the upper board. So they are soldered from one board to the other. If you want to remove one board, you have to desolder all these connections here, and also the connector on this side, and the wires that go to these test points here. And then you can open that and hopefully replace a failed transistor. So a lot of work here. Okay, let's turn it a little bit. I already mentioned this. Here are test points. This is a coaxial test point, so we have ground here on the outside and the measuring pin where you can put your oscilloscope probe in here. And you simply connect to all these test points to find out if something is wrong with this module. So these test points stick out when the module is inserted in the machine. And on the other side, we see the connector that plugs into the back plane of the machine. You can see one difference very clearly. So in 1965, they used silver contacts, and they have turned completely black over the years. In 1973, they switched to gold contacts, and they are still shiny and probably work like new ones. Here is another detail on the Cyber 170 module. You remember the CDC6000 had these coaxial test points. Here they have the test points directly on the PCB, which is of course a little bit cheaper to manufacture, so you don't need these coaxial connectors. You go directly to the board. Interestingly, they always have 2 PCB tracks for each test point here. You can see that a little bit better here. So it comes from here, goes back to here. I don't know if it was important to measure the timing exactly in the middle of this track. I don't know, but there are always 2 tracks for each test point. That's an interesting design feature. I have no idea why they did that. If you have an idea, let me know in the comments, as usual. Let's talk a bit about cooling. So these modules here, each one had its own slot. The whole slot was surrounded by cooled metal. So we had cool metal here, We have cool metal on this side, maybe not on the back side. There's the connector, and also the front here was screwed to the outside panel, which was also a little bit cooler than the inside. Okay, for the Cyber 170 they went a step further. I think we can see that here, yes. They added some aluminum strips that go under the chips. It's like a heat spreader, and they also have it here on the top of the board. So it's on both sides of the board. You have aluminum strips that go between the pins of the chips here, and the chips are sitting on this aluminum frame. This dissipates the heat to the side, where it is probably connected or very close to a cooled surface, or a cool surface was here when the module was slid in the slot. It made contact with this housing, and yes, that's how the heat was removed. The entire machine, at least for the 6000, was cooled with Freon, but the Freon doesn't come in contact with the electric parts here. It was just to cool the enclosure of this module. And here we have another part from the CDC6000 series. It's a core memory module, or storage module as they called it. It has 4 kilobits, the same arrangement as the memory before, but much smaller. And it has 12 of them. So there are 12 of these woven mats stacked together. And the whole thing then looks like that. So here you can imagine there are 12 core memory planes stacked together. Let's see what we have here. So we have a thick aluminum plate here. Yes, it's aluminum. It looks like copper, but that's a problem with anodized aluminum, especially if it's a little bit old. I assume that this was once a black coating, but it has turned to this reddish brown. So the whole part here is a heatsink that was very close to the cabinet walls where this module was pushed in, and it is also connected with the side aluminum panels here, which has a good thermal conductivity, and also the front panel, or the back side of the front panel here, is connected to this cold enclosure. And you can also see they added some substantial aluminum here. That's about, well, 2 or 3 millimeters. That is 3 or 4 millimeters. And now we can lift that off, and oh, it's thermal paste. And it's still soft. Okay, I'm surprised. I wonder if this was originally put in 1963, so that's probably the oldest thermal paste I have ever seen. I wonder, I wanted to find out when thermal paste was invented, but it seems that it's pretty difficult to find out. But obviously, they already had it in 1963, or it was added later because of a repair, or they spotted a problem here on the board and they needed some additional cooling. I don't know. There are also aluminum plates here and here, so the entire thing, all the electronics, is surrounded by cold aluminium. Also the outside here was very close to the enclosure of the computer rack. Yeah, and we have a lot of nice looking parts here. And of course put together also manually in the same way as I removed the cover. Someone installed it in that time. Okay, let's proceed to the next object. By the way, there is a reason why this is a 12-bit module. That means it has 12 memory mats stacked together. The CDC6000 series was a 60-bit machine, so with 5 of these modules you can store 60 bits at one time, and then the other 60 bits, so 1 bit, 12 bit of the 60 goes here, the other bits go to other modules, 5 of them you have 60. That's the reason why it is 12-bit wide. And we go a little bit further in time. This is from the year 1976. You can see it here, or here, or here on the chips. And that's not from CDC, that's a board from DEC Digital Equipment Corporation, once the second largest computer manufacturer behind IBM. Today part of the HP computer giant group. That's also a core memory. You don't see the memory because it has 2 layers, one board and the other board. And we will take it apart and see what this one looks like. Unlike CDC, DEC didn't solder the boards together. They have these pin and sleeve connectors here. Oh, you also can see the date here. October 4, 1976. So we know exactly when this board has its birthday. And we can separate that. Takes a little bit of force because there are so many pins, but they slip out relatively easy. Oops, that wasn't nice. Okay, and again here we have the same connectors on this side, and it lifts off like so. And what we see is nothing. There's another cover. Yes, it hurts a little bit to destroy these warranty seals, but on the other hand, I think warranty time is over. Et voila, here it is. The beauty of core memory. And you can probably already see this is constructed in a total different way, and it has much smaller cores, of course, because they have to be smaller to put so many bits in one plane. When I zoom in on this, that's the maximum I can do with my camera here. You can barely see individual memory cores, so these ferrite rings. They look like little donuts. But I have other pictures made with my Andon Star microscope, and I will show you that right now. if you just look at it, it has some similarities with an LCD display. So we have all the X drivers here, all the Y drivers down here, and also on the other board there are more drivers, and the whole electronics to get the bits in and out of this memory. Here at the bottom are the contacts for the bus. In this case it's called the Unibus. It has 1, 2, 3, 4, 5, 6 large connectors, and it's all the same connector for all the boards. So the CPU has these connectors, the memory has the connectors, the I/O cards has the same connectors. They all straight through connected with each other. Okay, let's do some theory. These are magnetic cores. Not from a memory, these are from cables, you know, this EMC stuff that prevents radiating all kind of electromagnetic waves from cables or otherwise. But I have this as an example how the core memory works. And these are the cores that are actually from a memory. You can see it looks like sand. They are tiny little rings. Through that core goes a wire, like so. And theoretically we already have a 1-bit memory. If we run a current through that wire, I stands for current, from the German word intensity, Intensität or whatever. When a current flows through a wire, it creates a magnetic field. And in this case, right-hand rule, current goes that way, magnetic field goes that way. So, see? Well, maybe it's a bit confusing with the arrow, but let's say so, huh? Okay, that's it. Is it right? Right-hand rule. That's the direction of the current, that's the direction of the field. If the current goes in the other direction, field goes in the other direction. If the current is strong enough, it makes a field that is strong enough to magnetize this ring. And if this ring is made of the right material, it will stay magnetized. So that's the first difference to these rings here. This will not stay magnetized because they are made from a different mixture of ferrite and they are not designed to get easily magnetized and stay like that. But the cores of the core memory are from a different material, and that's the first step of material science here, to make the cores with the correct properties. Now, if you have 2 bits of memory, we have a problem, because if we run a current through that wire, both of these bits will be magnetized. And if we have 3 bits, all 3 of them. And if we have 10,000 bits, 10,000 bits flipped from 0 to 1, or from 1 to 0, whatever. So how do we select the individual bits? The trick is to use a second wire, like so. That second wire goes in the same direction, and it will also have a current that goes in the same direction. but we only need half the current, because other half of the current goes here. And if we arrange that in a manner like so, I'm sorry, my wires are a little bit too thick, then we have an X, a Y and the X wire. Okay? If we have 1/2 of the current here, nothing happens, because we need full current to magnetize this ring. And of course we also have more wires for all the other rings, like so. Okay, let's say we want to store this bit. Then we let half of the current through that wire, and we let half of the current through that wire, E1/2. The sum of the two currents here is 1. 0.5 plus 0.5 is 1, and this magnet here, this ring, will flip its magnetization. The other two are not affected, because they only get half of the current, because here and here is nothing. Okay, that's how we write the memory. But how do we read it? So I made this 6-bit memory here. We have 2 Y wires, 3 X wires, 6 cores. We need a sense wire that goes through all that cores, all those cores. I go in from the same side on all cores, and again through the other cores here. Always from the same side. Now you can see why in the real memory these cores are placed in a zigzag orientation. So my cores are all like this. So my sense wire has to go so that it enters from above, goes down, enters from above, goes down. If this cores here were like so, I could simply make a loop, and then that, and so through the entire memory. Now, what's happening? How do you read one of these? Let's say we have a 1, we have a 0, we have a 0, 1, 1, 0. That means this core is magnetized in one direction. Let's say it goes clockwise, and the zeros are counterclockwise. Okay, I think you get it, huh? So we magnetize them with, well, our X and Y wires, half current here, bang. We have a 1, we have a 1, we have a 1. The other 3 are not affected, or not magnetized, or magnetized in the other direction. To read it, we need to write a 0. So that means something that turns it back into the counterclockwise direction. If it was a 1 and we write the 0, we get a pulse here in this wire, because this sudden change of magnetism induces a current into this third wire. It also induces currents into these wires, but that is not measured, that doesn't care, nobody is interested in that. But we get a voltage or a current spike here in this wire. Looks a little bit like so. If we write a 0 to a core that is already 0, we get nothing. So the result, if we get a spike, it was a 1. If we get nothing, it was a 0. Now we have a problem, because this core here is now 0. And this core remains 0, because nothing changed. We have to write that one back to that core. So after reading, we store our bits somewhere here in a little chip. We need some flip-flops or something to store one bit, that bit. And then we read the next bit. And we read the next bit. But before we read the next bit, we have to write that bit back. So we need a one flip-flop that stores this one, and then we can write it back to the memory and proceed with whatever we are doing. So that means writing goes directly, X wire, Y wire, half current, boom. Reading, X wire, right wire, writing a 0, looking is there a pulse or not, and if there was a pulse, write it back to that ring and continue. So that means core memory, when we are reading, is half as fast as writing. Just keep that in mind. We go into the details now. I forgot to mention that there are memories that have an additional wire. This additional wire is not needed for small memories, but it is needed for large memories that has more memory banks or memory planes. And the idea is, for example, if you stack this, you can put all these rings, all these X and Y lines in parallel. So let's say this is our plane number 1, then plane number 2 is connected to all 3 wires in the same manner, parallel. And if you just go and put current through these wires, you read all the planes simultaneously, and that makes no sense because you want to read individual bits. So what you need is an inhibit wire. I take this red one here and I just slide it in along with the Y wire here. I could also put it in with the X wire, that doesn't matter. So the idea of this inhibit wire is if we have a current going through that wire, but we don't want to read this entire row, for example, we give a current of I 1/2 to that wire. That cancels out the magnetic field of this wire, and nothing happens here, even if we apply the current through that wire. So we have 1/2 current here, 1/2 current here, but minus half current here. That makes only half current for this one here. In other words, with this inhibit wire, we can select different banks or different sections of the memory to read, but we don't need individual lines for each and every single core. That saves us a lot of wire and makes things a little bit easier to manufacture and also to handle. Okay folks, that's all for today. Thanks for watching.